me try to share my screen. Yeah, seems to be working. Okay, so good morning, everybody. Maybe good evening to a few people as well. Yeah, some people from Asia are joining as well. So so let me continue what I was doing yesterday, I think. The plan somehow was, let me just recall, the plan was somehow to describe some techniques from now on to prove operator norm convergence. So we had these examples of IID GU is here, IID Harrier is there, random permutations. So this example did not go through strong operator norm convergence, and so I already described this. I mean, briefly, at least the technology which was used by Mike Brannan to achieve this operator norm convergence in this context. Let me get back to the original results and start here. So techniques to prove operator norm convergence. So the most basic one, which is pretty much used in every a sub-proof somehow in every like then there are some branchings with various technologies kicking in, but somehow the one which is almost everywhere used is what is by now called the linearization trick. Linearization trick, which is that actually, so I will just write it that way. It is that proving operator norm convergence for, well, so that's already included in the definition for any non-commutative polynomial P is equivalent to proving spectral convergence. The convergence of something like this, of so maybe let me just specify here a little bit. My intention, which I had, I think, was with this x1 xk, so I will stick to this notation. So for any non-commutative polynomial P in x1 xk is equal to proving the spectral convergence of A0 tens. So now, okay, A0 tens A1 n plus A1 tens x1 n plus AK tens xkn towards the spectrum of the same with at the limit. So A0 tends 1 plus A1 tends x 1 plus AK tends xk. what we mean. So here I'm assuming that all the xi's are self-adjoint. Okay, I'm just going to assume this here, and this should be for every A0, AK, M by M matrices, say M by M matrices, self-adjoint, and this would be for any dimension M. And by convergence here, spectral convergence, I mean that so this is, yeah, so maybe I should have said here I'm assuming that the xins, they are also self-adjoint, and that now they belong to a finite matrix algebra. So this is maybe just to keep things simple, I'm going to assume that this is n-dimensional. So this is the identity of this algebra. Okay, actually, it doesn't have to be n here, but anyway, I will just keep it like that for now. And the convergence here means that now I have a spectrum, which is the set of lambdas for which lambda minus this is not invertible, and like that, like was here. And so this it means a convergence in the sense of Hausdorff distance. Convergence in the sense of Hausdorff distance and distance between compact sets. Compact sets. So the Hausdorff distance is I enlarge if I look at two compact sets, and if I enlarge enough one, it will be contained in the other, and conversely, and then this is also, so if I this is what is the minimal amount of enlargement that I need for one to be contained in the other, and conversely. So that's the Hausdorff distance, and we want this Hausdorff distance to tend to 0. So the thing here is that so this linearization trick. So this is due to Hager and Dorfenson, and Tor Björnsen. It initially we have to check the convergence, a problem of convergence of norm for a polynomial, so which is something which is of arbitrary degree, so which is not non-linear in X, and this is called the linearization trick, because now we say actually we just have to check some spectral properties, so which is norm slightly, like a little bit more than the information of the norm, but just for degree 1 polynomial. So the trade somehow is so the trade is that in exchange for that we have to accept to deal with matrix coefficients. So which is, and actually, so this version was given by Hager in their seminal paper of 2005, but there was an earlier version of this by Pizier in 1996, I think, around 1996, where he handled the case of xi being unitaries. Unitaries. And in this case, in a sense, it was even simpler, because it was enough to just look at the norm convergence. In this case, it was just something like this, which which was enough. So let's see. Yes, I'm just copying the same thing, and I just have to add here. I don't even have to define the Hausdorff distance. That's just enough. Right. So actually, subsequently in the work of Charles Bordenave and I, we use more PCS version, like which is lighter somehow than Hadoop noise version, because we don't actually, because we're working with unitaries, so we can afford to do that. Okay, and so then from now on, we just focus on linear on linear versions of on linear polynomials in x1 xn, or like of degree 1, let's say degree 1, because there is the identity, so they are not linear. So sometimes this is called linear pencils, though. So I will go very briefly. I will describe very briefly what Hagerup and Torbjørnsen are doing then. So Hagerup and Torbjørnsen, then they use matrix valued still just transform. Matrix valued. So here the matrix is this is the matrix of the coefficients. So where are they? They are here, right? So this is M, a matrix valued still just transform. So they have what they, so their still just transform is so they first take the random one, which is something like this, which is hn of lambda is the identity over m, that's the trace, the normalized trace over n of lambda times 1n minus this guy here, which they call Sn minus Sn inverse. And then they look at the expectation of this. So the expectation of Hn lambda is, they call it Gn lambda. And when n goes to infinity, they call it G lambda. And basically the kinds of results which they prove is something like this, is that Gn lambda minus G lambda operator norm is less than some constant over n squared. And here I have something else, but I mean, yeah, I will just write it down and say what matters from my point of view. So here we take lambda, which is yeah, so a matrix whose eigenvalues have positive imaginary parts, and so im lambda inverse. So I see they have a power 7, but there has been improvement subsequently. So let's just look. So first thing is they obtaining this is painful. I mean, you have to use in a very clever way repeated integration by parts. So sometimes this has been theoretized as Schwinger-Dyson equations, and actually I'm not going to talk about that. I mean, this is, I think this is well known to many people. I would just like to focus on the idea of how to, like on the somehow the analytic idea to prove a strong operator norm convergence. So let's say, for example, that I'm just going to draw some kind of try to attempt to draw something. So let's say that the spectrum of S lambda, has some components like this. Well, this will mean that G lambda somehow is analytic away from there somehow. And now if you look at Gn lambda somehow, what this, I mean, in my opinion, I would say that this 1/n square is the important thing, because somehow if you had one eigenvalue floating around far away from the spectrum, then morally, but you can make it rigorous, you would have some 1/n which kicks in somehow, like one eigenvalue would give, because you are normalizing things, it gives some kind of 1/n fluctuation. So this estimate here shows that actually you cannot have eigenvalues away from the spectrum. Somehow that's I would say that's an idea. So this rules out any eigenvalue away from the limiting spectrum. So I'm not going to say more about that. However, what I would like to say one word about. So this is okay. That's what I'm going to say about the technology required for the first example, and I would like to say a few words actually about the technology which is needed to prove the second example with random Harry intervals. So I think that this was probably the initial question by Haggop and Torbjörnsen, and it turns out that all the technology which I swept under the rug here works quite well for GUVs, so for Gaussian unitary ensembles, but it doesn't work so well for Harry unitaries, because basically there are no self-adjoints, and the integration by part techniques are not so well fit to this linearization trick which was developed by Haggop Tomlinson. So somehow I think kind of makes sense, because the Stieltjes transform is well behaved when the eigenvalues are on the real line. Okay, so so the case. So let's see. So this is here. So this is the example one. Let's say. Okay. So for two. So for the case of Harry unitaries. There were some earlier attempts by Camille Mal to somehow do things like take the real part and imaginary part of unitaries and try to repeat the Haggop-Torbjörnsen argument, but it did not work so well. And so together with Camille, we just made the following very simple single matrix observation, which I would like to explain. So observation. So this is what I could maybe call a lemma. So here, this is so this is by me and Camille. The lemma is the following. The lemma is about relating So now what we would like to deal with IID hereditaries. We already know, thanks to Hargroup and Torbenson, how to deal with GUEs. So how could we use one for the other? And the lemma says that if you take a positive epsilon, then you can find some polynomial which will depend on epsilon, so which is a C-valued polynomial, which has the property that given IID hereditaries U1 UD, maybe I should say, I should keep the track of the dimension. There exists IID GUEs, which I will call H1N HDN, which have the property such that with high probability, as n goes to infinity, and the limit sub of the operator norm of P epsilon HIN minus UIN is less than epsilon. So once you have this, basically, you are done. Because you know with Hargroup Thomason that this thing's conversion operator norm. So these things here will conversion operator norm. And so these things, they will almost conversion operator norm. They will converge up to epsilon in operator norm, but so you have one lim sub which comes up, but this is going to be true for all epsilon. So eventually these things will also converge, in operator norm. So this lemma actually allows to extend. So this, maybe I should write it like this. This lemma. So this lemma allows to extend the Hargroup turbulences results from IID GUEs to IID hereditaries. And maybe I could just say one quick word about how this lemma works, because actually this is just a single matrix trick somehow. So it brings very little in comparison to the original idea of Hargroup Torbenson. So the idea of proof was as follows. What we do is we pick a function, a smooth function P, let's say, no, P is not good. Yeah, why not? P from R to R. From R to C, sorry. And I will actually even say S1 to S1, which is included in C, which I would like to be increasing. So increasing doesn't really make sense, right? Because we learned in S1. So I mean, the argument is increasing. Maybe if I wanted to be precise, what I would mean is something that is, maybe I would like something that for all t, p prime of t over I pt, probably something like this, which would have to be positive, or something like this probably makes. So what I want the argument to be increasing. So somehow the idea is I want to wrap R around C. So I could write it like this. I could say that I wrap R around S1, and such that the push forward under P of the semicircle distribution, just this distribution over -2 and 2, is actually the uniform measure, on S1. So this is quite easy to do. I mean, you just take some cumulative functions with respect to the argument, take some inverse, and I mean that can be done. That can be done rather easily. And by the way, you are free to choose if you wrap once or twice or whatever. That doesn't matter either. So I have this smooth function, and now what I will do is I'm going to approximate this function. I'm going to approximate this function by P epsilon in norm, uniformly in norm, let's say over whatever, maybe over -2.1 and 2.1, like slightly beyond the -2 interval that kicks in here. And then what we do is we take our unitary matrix. Maybe we take like UI, like this, UI n, and we're going to diagonalize it. So we're going to write it like this. So this is a normal operator. It can be diagonalized. So this is going to be V, and this is going to be a diag of E I theta 1 I theta n, and here, so let's see, probably if I want to be consistent with what probably I have to do, let's see, maybe I should have taken here, I should maybe have requested that P of 0 is 0. Anyway, and so here I have V star, and let's say that theta 1, they are increasing like this, theta 1 and theta n, and this is between -pi and pi, something like this. And then what we do is we pick, so we pick random lambda 1 n bigger than lambda n, which are distributed according to the eigenvalues of GUE. So this is something which is a distribution which is well known. So the distribution is, so this is a vector in R to the n, and the distribution is proportional to exponential minus some lambda I square over 2 times product I less than j of lambda I minus lambda j square. So I just pick something like this. And now the solution, basically, the solution is you take HIN to be V diagonal of lambda 1n, lambda n V star. And that's basically the solution to the problem. What you can check is that the wrapping will work well. So it will not work well up to epsilon because I have some fluctuations here as well. But the fluctuations, they become more and more tame as n grows. And there are very good estimates on how the eigenvalues fluctuate globally here and how they fluctuate globally there. So let's say that maybe the estimate will be good up to 2 epsilon, something like this. And the last thing which remains to be proved is that when I diagonalize either a unitary Haar unitary matrix or a Haar like a GUE, the basis part and the eigenvalue part, they are independent. They can be chosen to be independent. So what we do now is somehow we replace the initial GUE which I got from here by a GUE in a basis that fits well for me. But since these guys remain independent, this is again a new GUE. And what I was able to do is from this and some additional randomness, I was able to cook up a GUE which satisfies this this kind of L-infinity transportation property. And so this procedure actually only depended on UI and some ancillary independence. So I am able to do this for U1, U2, and so on and so forth, and to have these independent HIs. So at the end of the day, I have managed to pick these people IID, and I can use Hagerup and Torbensen's result as indicated. So hoping that this it's a little bit, I mean, it's not extremely precise, but at least I hope the idea makes sense.
Benoit, I have a small question.
Yes.
So you demanded that P of 0 was 0. Do you need something like P of 0 is 1, or what's the normalization you're picking?
Sorry, I need what? I need?
You've chosen P of 0 to be equal to 0.
Oh, yeah. sorry. P of 0 is 1. Yeah. P of, yeah, sorry, yeah. Let me correct myself in a hypercritical way. P of 0 is exponential I0. Thank you.
I have a question to Jamie here.
Yes.
Yeah, it's so when you apply P epsilon to H, of course, you can move it into the eigenvalues, right? So you're saying
yes.
Epsilon of lambda I is somehow close to e to the I theta I, right?
Yes.
So those are, so you have, that's the thing where the 1 over, that's the thing that has to get small, right? That's the V goes away when you keep the norm. So how do you make that? So you take one distribution and you try and move it on to another distribution. So you're kind of measuring the distance between these two distributions somewhere, is that it?
Yeah. So what I'm doing is, so if you wanted, it could be possible somehow to insist. So it's I suppose ultimately it's so hoping that I understood your question properly. What it would be possible actually to try to do things simultaneously, like to take epsilon, which depends on n, and do everything at the same pace, like send everything to infinity, like send epsilon to 0 while you send n to infinity. So here what we just chose actually is to say, okay, we just fix epsilon, and then we have this kind of thing, and then it holds for all epsilon. So the point maybe, I don't know if this also goes towards addressing your question. This actually, if you look at the distribution of this, let's say from a measure theoretical point of view, this is extremely far away. Like maybe if you look at the total variation distance between this guy and that guy, they are very far away. So somehow, really what we really care about is that the operator norm distance is small. Yeah.
Okay, but then why can't you take, instead of taking the unitary U, take some other distribution and do this, choose a different P that takes the density of the semicircle law into some other density and just repeat this for any other operator?
Yeah, actually, that's what we are doing. So here I said you do it for I, you do it for all i's, right? You do it for 1, 2, and so on and so forth. Was that the question, or?
No, I'm just wondering what was special about okay, you had the uniform measure on the circle. That P
Yeah.
semicircle.
Oh, yeah. Okay. Got it. Yeah. So you're asking what would happen if I took some other distribution. For example, if we took, let's say some Brownian, let's say some Brownian unitaries or something like this, right?
Well, that's too fancy for me, but yeah, go ahead.
Yeah, that actually the same result works. Yeah, that's yeah. So that completely works. So here we just we just settle the hard distribution again. But actually, with I think with Todd Kemp and Antoine Dahlquist, we also studied the unitary Brownian motion that way. So yeah, this strategy is in principle powerful enough. Like you can do it for much more general cases. Yeah.
Thanks.
Okay, so that was example 2, and now let's try to look at. Yeah, so I would like to start. I will not have time to finish tonight. Random permutation. So actually, so example 3. So example 3. So here I wrote this is random permutation. Permutations. And I could say, and I will say, and more, because actually, what I would like to do is to describe. So, for example, one of the things which we proved, so we also proved, for example, this, the operator norm convergence for random matrices like this, for UN tensor Q10, so that is UNI tensor Q10, which are matrices in. So we proved a bit more than this, but let me just stick to that. In MN tensor Q times. So instead of taking hard unitaries, what you do now is you take hard unitary, which you tensor with itself many times. So it is very clear that you will have asymptotic freeness because you take a word and you look at the trace, and now instead of looking at the trace, look at the trace power q. So when you do asymptotic freeness in this case, you have to put it goes either to 0 or to 1. So of course, if a function goes to 1, its q's power goes to 1, and if it goes to 0, its q's power will go to 0. So somehow asymptotic freeness is trivial. It's trivial here, but strong asymptotic freeness actually is highly non-trivial. And well, roughly speaking, one reason is that we have much less randomness, so which actually relates also to the problem of random permutations. So, for example, one of the ways you could think about that is that if you would like to do some, if you would like to prove approximately, let's say, operator non-convergence. Let's say that you would like to prove operator non-convergence within within a factor 10, something like this. In this case, with Hager turbines, in the case above, I think you could do it. You could do it with some a concentration of measure and some net arguments. You could get some things done. Just because if I look at every entry of my polynomial, it converges. This if I scale it by a factor square root of the dimension, then it will be a sub Gaussian variable, and then if I make an epsilon net, the dimension fit well. And here, since I take the same variable, I would still have the same. The only scaling which would be allowed would be of the same, square root of n. However, here an epsilon net would be much bigger because the dimension is blowing up. So it's less clear somehow that we can obtain operator non-convergence with purely analytic techniques. So in both cases, when we have less randomness, somehow maybe that's somehow a catchphrase that if we have less randomness, then we should revert to moment methods. So originally, what is the moment method? So original moment method goes as follows. So I think this was developed by Furedi Olmos. Yeah, I mean, I would also like to quote Soshnikov for this, because he's really pushed it to some incredible. So Sinai Soshnikov. So the origin moment method is to evaluate. So for a matrix. Also, maybe here I could say Sn. Just to stick with the Hager Torbenson notation. The problem would be to evaluate the expectation of the trace of Sn to some degree L, which would depend of L simultaneously. And the thing is that if L of n is strictly bigger than the dimension in which the matrix lives, mistake, log of dimension, then this this will detect the largest eigenvalue. Somehow this will basically behave like the L infinity norm, this quantity. At least if I take the Lth root, if I take the Lth root of this will be basically the L infinity norm. So, but the problem though is that the problem somehow the problem is we don't know. We are not able to implement this simple idea, for multi-matrix model, multi-matrix models. So basically, we don't understand the combinatorics. See, the thing is, if you just fix L, then you understand what happens from the point of view of free probability. But if L goes to infinity, even though it does not go too fast, somehow, like when you have when you're studying many things, when you expand this growth exponentially, so exponentially, so at the end of the day, you end up having too many terms to evaluate. So it does not mean that the moment method does not work, because that's actually the only one which we're able to make to work. But it means that we have to modify it. We have to modify. So modified moment methods. And I think that what I should do, since I have 3 minutes left, is maybe I will just write down an equation and I will explain it during my third lecture. So what we do is we are going to consider the setup. So maybe I will just start with the word which I think we like now to call operator values. Operator valued non-backtracking operator. Non-backtracking operator. And the idea, very roughly speaking, roughly, but I will be more precise tomorrow, is that we replace the problem of studying the spectrum of A0 tens 1n plus A1 tens U1 and so on and so forth by study the spectrum of an operator which I will call sum for, okay, so here maybe I should, yeah, sure, sum for I not equal to minus j. So here this is going to be this will be, how many did I have? I had k of them, right? So between minus k and k of E I j tens B I tens U j. And so you see here, okay, so maybe I will just make one comment here. Actually, U minus j, in my notation, this is going to be U j star. So I will somehow I will allow to have U and U stars in my here. And I will not only allow it, I will be interested in having, so like if I don't have it, then I could put 0. But generically, I would be interested in looking at like something slightly more general here, where I also allow the stars there. And so this here is a matrix which belongs to, what did I say, to M times M n. And what I am doing here is that now this matrix here belongs to M. So this guy is still MM. I have not told what it is, but I will say next time. Times M n, which is here. So you see, I have some n's here. Maybe I should have said that. And here, this is, I am enlarging even further the matrix. So here, this is a well, I think it's a 2k plus 1 by 2k plus 1 matrix with M 2k plus 1. And the thing is that given AIs, let me just be rough for now. Given AI, there is a way to cook up some BIs such that the spectrum of this is closely related to the spectrum of that. And so at first sight, it looks like we did something crazy, but it is not so crazy because this works very well with moment methods. Unlike that, this is with moment method, this is quite crazy, but this works very well. And the reason is here, actually. The reason is here. It's because when I want to make some moments, as we know, we have to take some high powers. And when I take high powers, this is some kind of clicking a close. So it means that I cannot go back somehow. So this is non-backtracking. I will have lots of zeros which will kick in, and eventually the sums which we will have to handle will basically be not sums, they will just be products somehow. So we are making one additional trade. The first trade was somehow to go from generic polynomials to some linear polynomials by adding some matrix coefficient. And now we do the next trade somehow, which is, well, I'm still not happy with this because this is too difficult. So I will make this coefficient slightly more difficult somehow, but there will still be m by m matrices. And now somehow my moment problem will almost be a product of matrix problem. So that's and that's what so the plan for tomorrow is to tell a bit more about that, and then if time allows, outline two more techniques which have been developed even more recently to prove operator non-convergence. So maybe yeah, I'm way over time, so let me stop here.
For what? So I have one small question. You said the issue with this moment method was that it didn't work well with multi-matrix models, but aren't at that point you're analyzing just a single matrix, namely this SN?
Right, but this SN itself is defined as your A0 times something plus A1 times something, and then at the end of the day, given the structure that we have to expand. We have to expand it, and I mean that's the only way that we know how to compute moments. There are some weak formulas or something like this, and this is somehow the crazy part. If there was a more direct way, maybe this could work in it, but we don't really see that at this point.
Any further questions? Yeah.
So in this last point, you mentioned that you also prove strong convergence for powers of for tensor powers. There does
Yes.
it make sense to let the order of the tensor go to infinity with n? And
Yeah.
also
Yeah.
get-
Right. So. Yeah. So actually, I did not. Yeah, I wasn't very precise in my statement. The way I said things is, I said, okay, you fix Q, you fix the number of legs, and then this works. Actually, if we check in more detail the proof, we can go up to maybe, I think, log. What was that? Was it log n or log square n over log n? So I mean, it's or over log n. I mean, it's possible to grow the number of tensors slowly. Let's put it that way. But we have no sense whether, I think it's really an interesting question to check whether we could send the number of tensors fast. I think it's, you know, there are studies of Bourgain and Gambold which look more at, you know, at tensors going fast to infinity, and we don't we're not able to say something about that.
Do you expect Q being linear, still like allowing strong convergence?
Well, so the thing is that I was not extremely precise in my statement. The more precise statement somehow would be that when you take tensors, you have irreducible repetition that show up, and there is one obstruction. The obstruction is when you have some rank 1 irreducible repetitions. So for example, if you take, so I didn't mention the fact that you could take u times u bar, and then you would have the fixed point. You would have some fixed points. So we'd have the true repetition, and then this would rule out strong phrase. So what you have to do is you have to. So I think that what is possible is that if you remove all the rank 1 repetitions, then strong convergence could hold true. But you see, even if I take P, which is what? P, which is linear, as you mentioned, then at some point you will have the determinant repetition which arise. And in this case, probably it will create a problem for strong convergence. So, but if you remove that one, yeah, maybe that would work.
Okay, thanks.
We don't know though.
Let's thank Benoit one last time.